Hi everyone, I'm very excited to start this course. In our first lecture, we will talk about what is Cassandra and when we should use such kind of database. So starting with our very formal definition of Cassandra, Apache Cassandra is a distributed, decentralized, scalable and highly available NoSQL database. I know these are a lot of terms to digest at one time, so let's take them one by one. By distributed, it means it is capable of running on multiple machines. If you have large and growing data, obviously you cannot accommodate all your data on a single machine. In such cases, you need some kind of distributed database like Cassandra to shed your load across different machines. So that was distributed. By decentralized, it means it doesn't have any master-slave concept. Means all the nodes are identical. Like if one of the node goes down, the other can easily take its place. Also, there is no single point of failure. In master-slave, if the master goes down, the whole system gets crashed, right? But here, that is not the case. Because of the same two reasons that it is fault-tolerant and it has no single point of failures, the Cassandra is a highly available database. Now let's talk about scalability. By scalability, we mean that we can add or we can remove any node at any given point of time without or very little performance impact. Moreover, you don't need to rebalance any data. You don't need to do any manual intervention. Also, you don't need to restart any process. Everything happens in the background. So that was a brief. Now we should know when we should use such kind of databases and what are the use cases. If you have large and growing data, as we discussed earlier, you should think about some kind of databases like Cassandra, but hold on. Let's discuss what other things you must consider before taking any decision. If high availability is an important factor for your application, you want your application up at all the times, then Cassandra could be a good choice. If your data is changing, evolving, it's not a static data because static data could not be a good use case for Cassandra. If consistency is not a concern for your application, so Cassandra is an eventual consistent database by default. It means if you write something and read something out immediately, it is possible that the data is inconsistent. Though that consistency is tunable, we will talk about it later, but it comes with some performance impact. So if your application demands consistency, then think about it again. Cassandra could not be a good option for that. The last but not the least, if you want faster writes, then Cassandra has very high throughput for faster writes. So that was Cassandra in brief. Distributed, decentralized, highly scalable, highly available, and with eventual consistency and with faster writes. In this video, we will see how we can set up the Cassandra on our local Mac machine. So first of all, go to cassandra.apache.org download and then click on this 3.0.17. I have installed this particular version on my machine. Once you are on the page, you can download the tar file from any of the mirrors provided, maybe from the first link. So I have already downloaded this tar file on my machine. Once the tar file is there, you can extract it to any of your favorite folders. So I have extracted it under the application and renamed it to Apache Cassandra. So you can see all the folders under Apache Cassandra here. So now let's open a terminal and navigate to that folder where we have extracted it. In my case, it is application Apache Cassandra. So once you are there, you have to create two directories under it. One is the data and another is the Cassandra logs. So let's create it. Make directory data. So I have already created one, so that's why it's giving me error. In your machine, it will work fine. The second one is the Cassandra logs. Again, it's already existing on my machine. Once you create these two directories, then go back to the Apache Cassandra, go to the conf, and then open this logback.xml in some text editor. So you can see there are some variables called Cassandra Cassandra.log directory. So you have to replace this variable with the actual path of the Cassandra logs that you have created. So let me replace it. Just give me 1 second. Let me copy paste. This is the location for the Cassandra logs, and I have to replace all those variables. Cassandra.log directory. So I can replace all the variables here. Once I have replaced, I can close this one. Now the next step is you have to export you have to set up two environment variables. One is the Cassandra home, and second is you have to edit the path variable to add the bin directory into the path. So let me open nano bash underscore profile. You can see I have already added these two statements. You can add these two statements in your bash underscore profile. First is the export Cassandra home and then the location to your Apache Cassandra directory. And second is the export path. Add to the path variable the path for the bin. So after you export it, you can close this and then save it. Source and then bash underscore, give me 1 second, bash underscore profile. Now you can start the Cassandra server saying Cassandra -f. So it may take some time to start up this Cassandra machine. It is still starting. So meanwhile, open a new Cassandra terminal. Simple terminals where we can launch the SQL shell for this Cassandra. Once it is started, I can say SQL shell. So you can see we are under the SQL shell. So that is all for the setting up the Cassandra on the local Mac machine. In this video, we will see how we can install Apache Cassandra on Windows machine. So first go to cassandra.apache.org download. Once you are here, click on 3.0.17. There are many mirrors available. You can click on the first mirror. That will download a tar file. I have already downloaded this tar file in my downloads folder. You can see it is already there. You can extract this tar file to any of your folders. So I have extracted it under the D folder in installed folder and rename into Apache Cassandra. So once you are in Apache Cassandra, you have to create two folders. One is the data and another is the Cassandra log. After creating these two folders, you have to change one configuration, but first of all, let's copy paste the location for this Cassandra logs. After copying the Cassandra logs, go to the conf folder, edit the logback.xml with some text editor. You will see there are one variable called cassandra.logdir. So copy paste this variable and replace it with the value of the Cassandra logs folder that we have just copied pasted. So you just need to replace these slashes because it's giving me the backslashes and I need the forward slashes. After replacing it, click the replace all button. After this, save this file. Now we need to export to set to environment variable. Go to the environment variable tab, advanced system setting. Go to the environment variable. First of all, you need to add one Cassandra home and you need to put the value of the folder where you have extracted that tar file. And then you need to go to the path and add the bin folder to the path for this Cassandra home. After setting these two variables, you need to open a command prompt. Just open a command prompt. Go to the directory like the Cassandra home. After going to this directory, you need to start the, let me paste it, let me copy this Apache Cassandra location again and then paste it here. After going to this directory, go to bin directory and then execute cassandra.bat. This Cassandra.bat will start this Cassandra server. So it will take some time. Meanwhile, just open another command prompt. In this command prompt, we will open that SQL shell. That is the Cassandra shell where we can run our queries. Just give 1 more minutes to this one. So when it is saying starting listening for SQL client, you can type SQL sh. So this will open the Cassandra shell here in this terminal. Once it is under this, you can say describe key spaces to see if it is working. You can see it is showing the system key spaces. So that is how you install Cassandra on the Windows machine. In this lecture, we will look into Cassandra data model, discuss its various constraints, and then we will do some hands-on in SQL, that is Cassandra query language. It will be a lot of fun, so let's get started. In Cassandra, column is a most basic unit and is nothing but a name-value pair. Row is a container for columns referenced by a primary key. But important thing to note is that if any column has null value, we don't need to store that column. Let's take a right-hand side figure. In the row number 1, we have column 1, column 2, column 3. But in row number 2, we just have column 1 and column 4. So this type of architecture saves lot of space. Now a table is nothing but a wrapper for rows. So we have table, inside table we have rows, inside rows we have columns. The key space is, if you are from RDBMS background, we had database in RDBMS. Here in Cassandra, we have key space, that is nothing but a container for tables. And these key space doesn't reside on a single machine. These span over multiple machines. The next thing is the cluster. The cluster is container for key space. So that was the overall view for Cassandra data model. Now let's talk about what are the Cassandra constraints. The scalability comes with many constraints. As you know, in RDBMS, you might have heard about joins, foreign keys, there are flexible queries, but in Cassandra, you can't join two tables. There is no foreign key. You cannot refer from one table to another table because these two operations are very expensive in terms of distributed database. In addition, you can't do flexible queries. It means you cannot use any columns in the where clause. You need to understand your application first and model your queries in advance. So these are the various constraints that you should keep in mind while working with Cassandra. Let's do some hands-on on Cassandra query language. If you already know SQL, then SQL will look very familiar to you. With some constraints and with some differences, we will talk about them as we proceed further. So let's create our first key space. Key space is nothing just like the database in RDBMS. So when we say create key space, this is our key space name, first key space with replication. Replication is duplication of data across multiple machines to provide backup. So this replication factor decide how many copies of data would be there. If I say replication factor as 1, it means that there would be only one copy of data. If I say 3, it means 3 machines will be carrying the same data. And this replication strategy, we will talk about it later. So let's create our first key space. I'm going to copy paste all these commands to save some time. Okay. Let me describe key spaces. Let me see if that key space is successfully created or not. So you can see our first key space is created. There are some other system key spaces as well that are used internally by Cassandra. Now I'll be using this key space because I want to create my table under the first key space. So you can see now it is under first key space. Let's create a table called employee. It has employee ID, it has employee name, it has employee age, and it has employee ID as the primary key. The primary key here are little bit different than like RDBMS. We will talk about them in more detail in our next coming chapters. But here let's create this table for now. Okay, let me describe this table. Describe table EMP. Okay, this table is under the first key space It contains all the columns that we have specified. Along with that, it contains bunch of other properties. We will not be talking about them right now here, but we will be taking them in our next chapters. So let me clear the screen. Let me insert few values into that. I'm going to insert first value. It is employee ID is 20, name is Michael, and employee age is 30. Let me select read the values from EMP. Okay, it means this row is successfully inserted. Let me insert another value. It says the employee ID is 10, employee name is John, and the age is 28. So let me read the values again. Now you can see there are two rows. As in the SQL also, we can update the values here also. I want to update the employee table and set the employee age equal to 31 where employee ID is 10. So let me run this command. When I select, you can see the employee ID 10 has age is successfully updated to 31. Cool. Let me read the value with some where constraint. I want to read employee value where the employee ID is 10. Let me see if it gives me result. Yes, if it is having employee ID as 10, employee age 31, and John. But here is one more important difference. In RDBMS, you might remember that we can use any column in the where clause. It has flexible query. But in Cassandra, the where clause can have only those columns which are part of primary key or those having the secondary indexes on them. Let me take an example. Let me run one command that is not like this column name that is not a part of primary key. I said select star for EMP where employee name is John. So employee name is not a part of primary key. So it is giving me error that it cannot be executed. Either you use allow filtering. So I'll talk about this, why it is not able to take the columns, why it's not allowing us. So we will talk about them later on. Now I will be deleting the values. Let me clear the screen first. Let me delete from employee where employee ID is 10. Let me see if it has been deleted. Yeah, you can see the row containing employee ID 10 has been deleted. I can truncate the whole table also. Let me truncate whole employee table. Let me select again. So you can see there are no rows. It has been truncated. I can drop this table. I can drop the whole key space. Let me drop the whole key space. Drop key space and key space name, that is first key space. Okay. If I say describe key space, should say it doesn't exist. So key space, first key space not found because you are already in the first key space and it is saying it is not found because it has already been dropped. In this particular lecture, I will talk about Cassandra keys and how data is distributed across the cluster. So let's see what is a primary key. As you might be familiar that primary key uniquely identifies a record, but in Cassandra, it is not just that. In Cassandra, primary key is made up of two parts. First is the partition key and the second is the clustering key. So partition key decide how data is distributed across the nodes, which data will go to which node, whereas the clustering key decide how data is stored on a single machine. So how data is distributed? Every node is assigned a range of token that determines which row will go to which node. We will take an example that will make things more clear. Let's understand that every node is assigned a range of tokens. How these tokens are generated? There is a partitioner class which is having a hashing function called partitioner that is used to generate these token values. Let's take an example. I'm just taking this example for the sake of simplicity. In actual, token range are generated using some complex hashing algorithm. But for now, let's say we have a token range from 1 to 100 and there are 5 number of nodes in our cluster. And suppose these tokens are distributed uniformly across this node such that the node number 1 get token range from 1 to 20, node 2 get token range from 21 to 40 and so on. Let's say we want to write a row that has a partition key as employee ID 20. And suppose applying the hashing function or the partitioner on the employee ID 20 gives us 62. So this 62 means that this row will be mapped to node number 4 because it has a token range from 61 to 80. So every time any record that has an employee ID as 20 as partition key will always go to the node 4, either for a read or for a write request. Now let's talk about the clustering key. As we discussed earlier, clustering key determines how data is stored within a single machine. Suppose we have a row that has a partitioning key pk1 and clustering key ck1 and ckb. So the pk1, the partitioning key, will be stored first on the disk, followed by the clustering key, and then followed by the rest of the column. If multiple rows belong to the same partitioning key, they will be stored one after the another. But important thing to note is that the rows are sorted by the values of clustering key. In this exercise, we will understand clustering key and partition key in some more detail. So we are going to create a table called books by author. It has author name, it has published year, book ID, book name and its rating. Also, this table has a composite key. The column in the inner parenthesis forms the partition key and the rest of the columns in the outer parenthesis forms the clustering key. So here author name is the partition key, which means token will be generated based on the author name. So all the record for the same author will always go to the same machine. Also, publish year and the book ID are the clustering key, means data will be sorted based on that. But we have explicitly specified this clustering order that we want the publish year to be in the descending order and we want the book ID to be in the ascending order. It means we want the latest published books first. So let me create this table first. So let me describe table books by author. So you can see this table has been created under first key space. It has all the columns. It has the primary key as the author name as the partition key, publish year and book ID as the clustering key. And the clustering order is that we want the publish year to be in the descending and book ID to be in the ascending order. Let me clear the screen first. And now we are going to insert few values. I am going to insert the values for author James Patterson. So first is I am going to insert a book published by James Patterson in 2009 called Witch and Wizard. Now I am going to insert the book published by the same author James Patterson in 2008 called Cross. So let me copy paste again. And the third row I'm going to insert is the book published by the James Patterson in 2018. So let's select star from books by author. Let's see what it returns. So as you can see, though I have inserted 2018 book at the last, but it is at the first because we have mentioned that we want the publish year to be in the descending order. And the book ID, we are not able to find out whether it is ascending or descending because it is some hexadecimal value. Why it is hexadecimal? Because we have used UUID as a data type. That is a new type of data. Maybe you have not seen it earlier, but we will discuss about it in our next chapter. So now we are going to read our data. In our last hands-on exercise, we said like if we want to use the where clause, the primary key has to be the part of where clause. But in precisely, partition key has to be part of the where clause, because in order to determine the machine on which the data will go, we need that partition key. If it is not there, it will have to search all the nodes in the cluster. That will be very slow and inefficient. So let me run this query first. It says, I want to select from books by author where author name is James Patterson and publish year is less than 2009. So it give me this row. That is fine. Suppose I change this query and I remove the partition key from here. And I just say publish year is 2009. So it tell me I cannot execute this query because it may involve data filtering and thus unpredictable performance. But if you still want to run such kind of query, you can do so by using the allow filtering clause. So I can say allow filtering and it give me the result. But the problem is it will be very slow, it will be very inefficient. The another important thing is the use case of clustering key. We can apply the range queries on clustering keys since they are sorted. As we have seen in the last this one, we said the publish year is less than 2009 and I can say publish year is greater than 2017. I don't get anything, right? 2018. Since not. So publish year, I have what data I have is select star. Let me check the data first. Select star from books by author. So I want this row, this particular row. Publish year has to be greater than 2008 and less than 2018. So let me see that. Greater than 2008 and publish year is less than 2018. So it should give me 2009. So we can use the range query. But can we use the range query on other column that is not a part of clustering key? So let me clear the screen first. Let's see. Let me take this query. It says that I want the books data from books by author where author name is James Patterson, publisher is less than 2009 and rating is greater than 4. Now rating is not a part of clustering key. So it is again giving me this error that I cannot perform this query. It could have a unpredictable performance, but I can say allow filtering though, but it will be inefficient. So it is giving me the result, but the problem is if it is not a part of clustering key, it has to sort all the data on that machine again and give me the results. So that was overall view of the partitioning key and clustering key. Thank you. In this lecture, we will see Cassandra's various data types. So let's see the first one, numeric data types like int, big int, tiny int, float, decimal that are used to represent numbers in different format. So nothing is new here. These are pretty conventional. And again the textual data type like text, varchar that are used to represent the character string. So I'm not going in much detail about these conventional data types. What I'll be covering will be the Cassandra's new data type. So next one are the collection data types like set, list and map, and we will see example of them when we will do our hands-on exercise for this particular lecture. Other data types like boolean, blob. Blob is a binary large object that is used to represent any arbitrary array of bytes, and boolean is something that represents true or false. Now we have some new data types like UUID, time UUID. Let's talk about them. UUID. UUID is a universally unique identifier. It is 128-bit hexadecimal value and is a unique random number that is generated in a distributed environment to prevent the duplicates. And Cassandra provides us with the convenience functions like UUID that generates this universally unique identifier. The next is the time UUID. Again, this is a unique identifier that is generated based on the MAC address of the computer plus the system's time and a sequence number. Again, this prevents duplicates, and Cassandra provides us with various convenience functions like now, date of, Unix timestamp of to generate this time UUID. So let's do the hands-on exercise for this one. Let's start with our first data type called UUID, that is a universally unique identifier. I hope you remember in our last lecture, we created one table called books by author. Let me describe that table once again for you. So it is describe table books by author. As you can see, there was a column called book_ID whose data type was UUID. Now I'm going to insert one more row into this table for the author Michael Anderson, and I'm going to use the UUID function provided by Cassandra that generates this universal identifier. So let me copy and paste. Now we will select and read the value that has been generated. So I'm going to select star from books by author where the author name is Michael Anderson. So you can see under book_ID a hexadecimal value has been generated by this UUID function. So let me clear the screen first. Now we will talk about the time UUID. Time UUID is again a unique identifier, but it is generated from the value of the MAC address, system date and a sequence number. So what we are going to do, we are now going to add a new column into the same table. What I am saying is that alter table books by author, add a new column called book_time UUID whose data type is time UUID. So let's describe this table once again. Describe table books by author. As you can see, this new column has been added into the table. Now we are going to insert a new row for the author Tony, and now I am going to use the now function that has been provided by Cassandra to generate this time UUID. So let me copy paste this. Now we will select star from books by author where the author name is Tony. Let me expand the screen to show you. As you can see, under the book_time UUID, a hexadecimal number has been generated for this time UUID data type. So that was time UUID. Now let's see some collection data type. First of all, we will see set data type. Set data type stores a collection of elements. There cannot be any duplicates. If you insert a duplicate value, it will be overridden. And the insertion order is not maintained. So what I am going to do, I am going to add a column into books by author. I am saying add a new column called emails whose data type is of type set. So let me describe this table and see if that column has been added. So as you can see, this column emails has been added into the books by author. Let's clear the screen. Now what we are going to do, we are going to update an existing row where the author name is Michael Anderson. So what I am saying, let me copy paste it first. I am saying update this table books by author, set the emails to michael@gmail.com where the author name is Michael Anderson and the publisher is 2017 and so on. So let's see if that has been inserted or not. Select star from books by author where author name is Michael Anderson. So as you can see, the email address has been successfully added into the row. we can add some more email address to the same row. Here I am saying I want to update this table. I want to set this email address, keep the existing email and add one more address. I want to address michael@anderson@gmail.com to the same row. Now let's select again and see what happens. Now you can see 2 email address has been added. Like we can add email address, we can delete email address from the set as well. So here I am saying set emails equal to emails minus michael@gmail.com. I want to remove this email address from the set. Let's select star again, and as you can see, the michael@gmail.com no longer exists in this set. So let me clear the screen once again. If you want to empty the whole set, you can do that also. Here you can say update this table. Set emails is equal to empty parenthesis. So it will delete the whole set. As you can say, now it is a null value. This was all about the set data type. Now we will discuss the list data type. List data type also contains list of element, and by default the values in which we insert are maintained and duplicates are possible. So now what I'm going to do, I'm going to add a new column called phone numbers, and it is of type list. Let's describe this table once again. Describe table books by author. As you can see, this phone number has been added. Let me clear the screen once again. So now what we are going to do, we are going to update the same row and we are going to set the phone number for the author. So I'm saying set phone numbers is equal to some phone number in this square bracket. So let's select. So select star. It shows that this phone number has been added. If I want to add some more phone number, I can do so using the plus operation. Give me 1 second. So let's add some more phone numbers into the same row. Here I am saying set phone numbers is equal to phone numbers, keep the existing phone numbers and add one more phone number into the same list. So when I say select star, you can see the comma separated list. Here are now 2 phone numbers. Also, we can delete some phone numbers as well using the subtract operation. Let's say select star. As you can see, the phone number has been deleted. Also, we can access the phone number using the indexes. Suppose I want to delete the first phone number from the list, so the index for that phone number is 0. Let me copy paste this command first. So what I am saying, delete phone number whose index is 0 from books by author, where author name is this, and so on. So let me select again, see what happened. Now as you can see, let me expand the screen first. The phone numbers is now null because there was only one phone number and I have deleted that as well. So the list contains null. The last kind of data type, collection data type, is map. It is nothing but a key value pair. So I'm going to add a new column called family, that is a key map of text and text. So we are going to update the same row here also. I'm saying update books by author, set family equal to, the key is wife of author is Sanya, the key is sibling of author is John, where author name is Michael Anderson. So let me select again. Let's see. So as you can see, this map has been added into the row. So that was the map. In this video, I'll talk about replication. As the number of machines grows in a distributed system, hardware failure is unstoppable. and just keeping one copy of data would be a stupid idea. So replication is a must for high availability. So there are two things to replication. One is the replication factor and the other thing is the replication strategy. So replication factor decide how many copies of data would be there. Suppose if I say the replication factor is 3, it means 3 copies of data would be there. 3 nodes would be carrying the same data. And replication strategy decides where that copies will stay on what all nodes. So when we created a key space, I hope you remember, we created a key space and we said with replication. The class, this defines the replication strategy and this second thing defines the replication factor. So there are two strategies. One is the simple strategy and one is the network topology strategy. We will discuss that in our next slides. Let's talk about our first replica placement strategy called simple strategy. In this, the replicas are placed at consecutive node. Suppose we have a replication factor of 3. Let's see how it happens. The client initiates a write request with the coordinator node. As we have discussed earlier also that coordinator node based on the partitioning key derives a token value. And suppose that token value get maps to the node number 3. So this node number 3 will become the primary node for that data. Now if the replication factor is 3, we know that 2 other nodes should be there who should carry the same data. So how this coordinator decide what 2 other nodes? So if the strategy is a simple strategy, the consecutive node will be carrying the replicas. So the consecutive node to 3 is 4 and 5. So these will act as a replica node for the data and coordinator will send the request to these 2 nodes as well. So that was the simple strategy with the replication factor of 3. Let's talk about our next replica placement strategy called network topology strategy. So this kind of strategy is used in case of multiple data center. And the important fact about this strategy is it allows us to specify different replication factor for different data center. Let's see this create key space statement. It says use the replication strategy as network topology strategy, and for the data center USA keep the replication factor as 3, and for data center EU keep the replication factor as 2. So let's see with the help of diagram how it happens. Suppose the client initiates the write request with the coordinator. So as we discussed earlier, the coordinator will find the primary node and the replica node, the consecutive node to primary node, and send them the request. Also, this coordinator node will find a remote coordinator in the Europe data center and send it a write request. So this remote coordinator will find a primary node in its local data center. Since the replication factor is only 2, so it needs one more node which will act as a replica node. So that consecutive node will be 3. So this remote coordinator will send the write request to these 2 nodes as well. So that is how the network topology strategy works. In this video, we will talk about Cassandra consistency. As we said earlier, Cassandra has tunable consistency. It means we can increase or we can decrease the consistency level. But doing so comes with a performance impact. Also, we can configure the consistency for the read and the write operations separately. But first of all, let's understand what is a write consistency and what is a read consistency. So write consistency means the number of replicas on which the write operations must complete before returning the success back to the client. And read consistency means the number of replicas to check for consistency before returning the data requested by the client. So let's take a wider look at the write consistency first. Write consistency has 4 consistency levels. Level 1, all, quorum and local quorum. Let's talk about them one by one. By consistency level 1, we means only one replica node need to complete the write operation in order for request to succeed. So let's say we have a client who wants to initiate a write operation with the cluster. It may connect with any node in the cluster and that node will act as a coordinator node. Suppose the client sends a request to node number 5. So the 5 node will become the coordinator node. And based on the partitioning key and the replica placement strategy, this coordinator node will decide on which all node the data has to be written. Suppose it find out the data has to be written on node number 1, 2 and 3, so it sends the request simultaneously to all 3 nodes. But as soon as it receives the success acknowledgement from any one of the nodes, suppose the node number 3 says that it has completed the write operation, it sends the success acknowledgement back to the client without waiting for node number 1 or node number 2 to complete. So that was consistency level 1. The consistency level all, this coordinator node will wait for all the replica nodes to complete. So it will wait for node number 1, 2 as well as 3 before sending the success acknowledgement back to the client. And with the consistency level quorum, if we have a quorum value of 2, so this coordinator node will wait for exactly 2 replica nodes to complete. So that was the one all and quorum. Let's talk about local quorum. We know that Cassandra can span over multiple data centers. Suppose we have 2 data centers, and if we say local quorum is 2, it means 2 replica from the same data center as where the coordinator node resides should complete the write operation before the coordinator node can send the success notification back to the client. So let's understand with the help of a diagram, it will be more easy. Say we have a client, it sends a write request to the coordinator node. The coordinator node is in data center 1. So this coordinator node will send the write request simultaneously to all the replicas in data center 1 and data center 2. But as soon as it gets at least 2 write complete respond back from the 2 replicas from data center 1, it sends the success notification back to the client. So it will not wait for the data center 2 replicas to respond, it will wait only for the local replicas to respond. So that was the local quorum. Let's talk about one more consistency level called each quorum. So in the last local quorum, we saw that the coordinator node will only wait for the local replicas to respond. But in each quorum, if each quorum value is 2 replicas per data center needs to complete the write operation before the coordinator node can send success notification back to the client. So if the client sends the write request to coordinator, it sends the request to all the nodes in the data center 1 and data center 2, but it will wait for response from both data center 1 and data center 2 before sending the success notification back to the client. So that was a difference between the local quorum and each quorum. In this video, we will talk about read consistency. Read consistency have same consistency level as the write consistency, namely 1, all, quorum and local quorum. But this read consistency functions a little different from write consistency. We will see how. So let's take an example of the consistency level 1. In consistency level 1, the coordinator node will not send request to all the replicas node. Instead, it will send request only to the fastest node. And how it get the information about the fastest node? Let's see. Suppose there is a client who initiates a read request with coordinator node. The coordinator node consults the snitches program. Now snitches program is a program that has all the information about the network topology and it knows the fastest route or the nearest node. So it gives the information about the fastest node to the coordinator node. Suppose it tells the coordinator node that the node number 3 is the fastest node that can provide this requested data. So the coordinator node will send the request to node number 3, and as soon as this node number 3 return the requested data, it sends the data back to the client. But in the background, it will check for the consistency in the other replicas node. Suppose the node number 1 and node number 2 also contains the data for this requested data. It will check if this data is consistent or not. If it found that the data is inconsistent, the coordinator node will initiate a read repair request in the background. So that is how the consistency level 1 for read works. Let's see the quorum consistency. If the quorum value is 2, it means the coordinator will send the read request to 2 of the node, one to the fastest node to get the actual data and one to the second fastest node to get the hash of data. Why hash of data? to save some network bandwidth, because transferring data over the network is very expensive. So let's see how it happens. Suppose the client initiates a read request with the coordinator node. So this coordinator node consults the snitches program to get the information about the fastest and the second fastest node. And after that, it sends the request, the read request to the fastest and a digest request to the second fastest node. Once it gets the data and hash of data back, the coordinator node compares these two data to check for the consistency. If they matches, then the coordinator node is good to send back the requested data back to the client. But what if they don't match? What if they are not consistent? In that case, the coordinator node again send a read request to the second fastest node to get the actual data instead of hash of data. So once it gets the actual data, it merges these two data based on the latest timestamp of the column and then send back the merged data back to the client. And also now the coordinator knows that the nodes are not consistent and the data don't match. So what happens? It initiates a read repair request in the background to cope up with these inconsistency. So that was the quorum consistency. Let's see the local quorum consistency. The local quorum is used in case of multiple data center setup. Suppose we have two data centers and the local quorum value is 2. In this case, the coordinator will send the read request to two of the replicas in the same data center in which the coordinator itself resides. So it will not communicate with the data center 2. So let's see, if the client initiates a read request with the coordinator node, all the process remains the same as we discussed in the quorum. Like the coordinator consults the snitches program to get the information about the fastest and the second fastest node to get the hash of data and the actual data. And then it compares the data and send back client the requested data. But in the background, it checks for the inconsistency across the data centers as well. If suppose there are a few replica nodes in the data center 2, so it will check for the inconsistency in the background, and if they are found inconsistent, so this coordinator node will initiate a read repair request. So that was the local quorum. As far as each quorum consistency is concerned, it is not supported for read because it will be very expensive to wait for the request response from the data centers 1 and data center 2 to fulfill the read request. So that is not supported in case of read. In this video, we will talk about something very interesting that happens inside the Cassandra cluster, and that is gossiping. And we will see how the state information floats around the cluster using this gossip protocol. So every node in a cluster gossip with each other like we human beings do, and they also love gossiping like us, but the only difference is they don't lie. They only tell the truth and they share the state information about each other. Suppose we have a 6-node cluster and say the node A starts gossiping with node D. And as soon as the node D respond back, the node A saves the state information about node D. Another second, say the node E starts a gossip session with node A. Now node A will send the state information about itself as well as node D to node E. So this way the information floats very fast and very efficiently around the cluster, and within minutes the cluster is up to date with the state information. This is a never-ending process. Every second, every node gossips with each other. So, but what happens if a node doesn't respond back? What does the starting node do in that case? Say, in that case, the starting node will not mark it dead or alive straight away, but assigns a suspicion level to that node. Suspicion level is something that indicates the probability of node being dead, and that mechanism is called the Acular Failure Detection Model, which means instead of doing the binary assessment, saying dead or alive straight away, we assign a probability number to the node, which determines the probability of the node being dead or alive. Also, there is another part to this gossip protocol called gossiper class. This gossiper class initiates a gossip session with any random node in the cluster. Say this gossiper initiate a gossip session with node F. So this node F will send back all the state information it carries, and this gossiper class maintains a list of state information of nodes locally. So it updates that list. So that was all about the gossip protocol. In this video, we will see how the write happens on a single machine in cluster. So we have seen all sort of things, the replication, consistency, how the write happens across the cluster, but we have not seen how it happens on a single machine. So let's see. When a write operation comes, it is written direct straight away to commit logs. Commit log is a disk file that is used for the crash recovery purpose. Means if the system crashes, the commit log can ensure the data is not lost. And there is only one commit log per machine. After the commit log, the data is written to a mem table, that is an in-memory data structure. Each table has a specific mem table. But we know the memory is limited. We cannot keep all the data in memory. So when the mem table reaches some threshold value, then the content of these mem tables are flushed to the SS table, that is again a disk file. And then a new mem table is created for that table that was flushed. Now these SS tables are immutable files. We cannot change the rows once written to this disk. So you might be wondering that if they are immutable, then how the delete and update happens in Cassandra. So the important point to note here is that every operation, either delete or update, is a write operation. It's not like a delete or a update operation. So we will see in more detail how they happens when we will be discussing the compaction technique. So that is all for now, how the write operates in Cassandra. In this video, we will talk about Cassandra storage. In our last video, when we were talking about writes, we have seen mem tables, commit log and SS table. But now, we will take a deeper look into the components of SS table and few other Cassandra storage components. Starting with our first in-memory data structure called Bloom filter. Each SS table has a Bloom filter associated with it. And this Bloom filter tells whether a particular partitioning key is present or not in that SS table. But be aware, sometimes this Bloom filter gives us a false positive. It can say yes that a key is present, but when in actual you go and scan that SS table, you will find out the key was actually not present. So that was Bloom filter. Let's talk about our another in-memory data structure called row cache. So row cache caches subset of rows in the memory. But we can configure how many rows we want in the memory at a particular given time. Like we can say all means all rows should be cached. We can say none means we don't want any rows to be cached. Or we can say any value n means I want 10 rows to be cached. I want 20 rows to be cached for a partitioning key. Though it provides with some performance improvement with the read operation, but caching all the data into the memory is kindly discouraged in a production environment. Let's see our another in-memory data structure called key cache. Key cache is a key value pair where key is the partition key and value is the location of data on disk for that particular partition key. You may disable or enable this key cache because it may provide you with some performance improvement for the read operation, but it may slow down your system for the write operation. So depending on whether your database is a read intensive or write intensive, you may disable or enable this key cache. We have been discussing about SS table from so long, but we need to understand one thing, that SS table is not a single entity. SS table has many components associated with it. In the first section, we discussed about Bloom filter, that is the part of SS table. And now is the data file. Data file is nothing but the actual data that is stored on the disk. It has partitions, it has rows associated with that partitions, and these partitions are actually in the sorted order. Let's see the another component of SS table called partition index file. This partition index file is the location for the row in a data file that we have seen earlier for a particular partition key. Say we have the partition key 7, we have the partition key 2, and we want to know what are the location of this partition key 7 in the data file. So this index file can give me that location. Let's see yet another component of SS table called partition index summary file, which is an in-memory data structure. It is nothing but a summary for index file that we have seen earlier. So this index summary file contains a range of partitions, saying start partition is partition key 7 and end partition is partition key 125, along with a location that maps to the location of this ending partition in this index file. So why we need such kind of data structure? So this kind of data structure is required to improve the performance and to read this index file more efficiently and more speedily. So that was the partition index summary file. I know we have done a lot of things in this lecture, so let's do a quick recap so that we can retain the concepts more efficiently. So the first thing was the Bloom filter. The Bloom filter tells us whether a particular partition key exists in SS table or not. The next is the row cache. It is nothing but a cache of rows. We may cache all the rows, we may cache none of the rows, or we may cache some of the rows. The next is the key cache. It is nothing but a key value pair that maps the partition key to the location of data on the disk. The next one is the actual data, that is the data file. That is nothing but the partitioning key along with the rows associated with the partitioning key. Partition index file again maps the partition key to the location of data on disk. You may see the key cache and partition index file seems very similar. So we will see how they are used when we will be doing the read operation. The next one is the partition index summary file. It is nothing but a summary for the index file to improve the performance. That was all that we have covered in this particular lecture. In this video, we will see how a read happens in a Cassandra. As we have already gone through all the Cassandra storage components, so now understanding this read operation would be simple. For this scenario, let's assume the data for which we are searching is not present in mem table. So if the data is not there in mem table, then we have to look for the data in SS table or the other data structure that we have discussed in the last chapter. Say we have a read operation for a particular partition key. The first place where we will be searching for the data for that partition key will be the row cache. If that row cache is enabled and we found the data in that row cache, then we can return the data straight away to the client. But if the row cache is not enabled or we don't find the data in the row cache, the second place to look for the data is the Bloom filter. So we need to search for that partition key in this Bloom filter. If we don't find that partition key, we have to scan for the next Bloom filter of the next SS table until we find the partition key. The next, after we find the partition key from the Bloom filter, we need to search that partition key in the key cache. It is nothing but a key value pair where key is the partition key and value is the location of data on the disk. If that partition key is present in this key cache, it can give me the data, location of data on the data file, and once I get the data, I can return the data back to the client. But if this partition key cache is not enabled or the data is not found in this key cache, then the next place we need to look for is the partition index summary file. This partition index summary file will give me the index for the partition in the index file. I know these are a lot of items to remember, but just take a deeper look. We have already discussed all these components in the previous lecture. So this partition index summary file will give me what? It will give me the index for the partition in the index file. And once we get the index for the partition, I can get the location for the data for that particular partition key. And once I get the location for the data, I can return the data back to the client. So that is how, when the mem table is not carrying the data, that is how the data is read from the SS table or the other data structure like row cache or the key cache. But if the data is present in the mem table, then we need to merge the data in the mem table with the data we found in the SS table before returning back to the client. So that is how the read operation works. I want you to take a look at this flow diagram again and again until unless you don't understand it completely. So that is all for the read operation. In this video, we will talk about compaction. Why we need compaction is because the flushing of data from mem table to SS table is a continuous process, and it may end up creating thousands of SS table lying on the disk. So scanning those SS table during the read operation would be a tedious task. So we need some kind of compaction so that we may decrease the number of SS table and then improve the read performance during the scan process. So what the compaction technique does is, it merges the data based on the partition key between the two SS table. Also, it keeps the data with the latest timestamp so that we don't have a stale data lying with us. It removes the rows with the tombstone. So tombstone might be a new term for you. What is tombstone? If you do a delete operation in a Cassandra, it doesn't delete the data straight away from Cassandra. Instead, it associates a tombstone with that row with some expiry time. So what does that mean is that during the compaction operation, if the compaction find a row with some tombstone and its time has been expired, so that row will not be propagated further. So that is what tombstone is. Also, the compaction technique deletes the old SS table once it has created the new compaction table. So let's see, we have SS table 1 with the partition key 1, 5, 7 and 11th partition key is associated with some tombstone and 20. There is another SS table 2 with 1, 5, 8, 13 and so on. So let's see how the compaction happens. The partition key 1 from the SS table 1 will be merged with the partition key 1 from the SS table 2 based on the latest timestamp, and the compacted SS table will get the latest data for the partition key 1. It may happen that the data in the compacted SS table have more rows if more inserts are there. It may end up having less rows if more deletes are there. So that is how. The second similar way, the 5 will be merged with the 5 from SS table 2. 7 will go straight away to the compacted SS table because there is no rows for the partition key 7 in the SS table 2. So there was no update, nothing new for the partition key 7. 8 will go straight away to the compacted table. 13 will go straight away. For 11th, since there is a tombstone associated with, suppose the expiry time has been expired for this row. So this row 11 will not get propagated to the new table. So 20, based on the latest timestamp, will be propagated to the SS table, and 23 will be straight away copied to the compacted SS table. So that is the very simple scenarios how the compaction takes place. There are many techniques to compaction that we will not be covering in this particular course. But if you want to read, you can go on net and check what are the various compaction techniques that are available in Cassandra. In this video, we will see how we can connect to Cassandra using the Java driver. If you are not familiar to Java, don't worry, just stay with me, as it will not be very much difficult if you know any of the programming language. First of all, open the Eclipse program. Eclipse is an IDE for Java, by the way. If you don't have Eclipse, Java or Apache Maven installed on your system, just look at the resources attached to this lecture, because I have given some installation step for Mac or Windows machine if you don't have these in place. So first of all, let's create a Maven project. Say new, other, say Maven project. Click this, create a simple project and say next. In the group ID, type anything like com.cassandra.sample, and in the artifact ID, say we are saying Cassandra sample, and then click finish. Once the Maven project has been created, you can see there is a pom.xml. Open the pom.xml. We need to add the dependency for the Java driver. Go to any of your browser and type Maven Cassandra data stack Java driver and open the first link. And then click on this 3.6.0 and copy paste this. So it will give me the dependency for the Cassandra driver. So here I am saying dependencies, and then under the dependency I am going to add the copied dependency. When you will say save, it will take some time to build the project. After that, let's go to the Java folder and create one first Java class. Say I'll name it Java Connector. And I'll click this public static void main for me, as it will create this method by default, and click finish. So this is my first Java class. What I am going to do in this class is I am going to connect to my first key space that I have created in my earlier lectures. So there is a Cassandra node running on my local machine. There is only one node, and I have already first key space as the key space created for me, and inside that key space I have a table called EMP. So I'm going to do something with that. First of all, let's create a connection with that localhost. So I'll say cluster. So you'll see there is some error coming. Cluster. So click here. You can import com.datastacks.driver.core.cluster. So this cluster object can help us connect to our local node. Say builder dot add connection point. Here we will say 127.0.0.1, and then we will say build. Once it is clear, let's create a session object out of it. Let's click here first. We can import the session object as well. Say cluster dot connect, and inside connect we have to give the key space with which we want to make the connection. Here I want to say first key space. So this will create a session with my first key space in my local host. Now I'm going to do some queries using this session object. I can say execute. I can say insert. Let's see what's there in the employee table as of now. So you can see I can say select star from EMP. You can see there is nothing. There is only 3 columns: employee ID, employee age, and employee name, and there is no rows inside that. So what I'm going to do, I'm going to insert one row. Insert into EMP, EMP ID, EMP name, and EMP age. And then values, I can say 10, name is John, and age is 30. Let's save and run this. Right click and run as Java application. Let's see what happens. So let's go to the background SQL shell again, and let's see what has been created. So I'm going to fire this query again. Now this time the row that we have created from our Java program has been inserted to Cassandra. We can do one more thing here. We can display the results here itself. I can say result set results equal to session dot execute and I can say select star from EMP. Again we need to import the result set, this one, com.datastacks.driver. So now I'm going to navigate through this result set. I'll say row result. Let's check this one. Import row as well. And now I'm going to print this on my console. System.out.println, and I'm saying employee ID is row.get int emp_it. Similarly, just copy paste this system.out.println command. Copy paste here. I'll say employee name is, this time it is a string. So I'll say get string emp_name. And similarly, just copy paste one more time and say employee age, and this is emp_age. Save this program and then right click and run as Java application. Let's do it one more time, Java application. So you can see the results are displayed on the console itself. So this was the first lecture about very simple queries. In the next few lectures, we will see how we can do some more stuff with the Java driver. In this video, we will see how we can use prepared statement. Instead of passing values like this, prepared statement can be used to bind the variables from outside in the queries. So let's say I'm going to create one method called private void add employee, and this method is expecting 4 arguments. One is the session object, and then the employee ID, employee name, and finally the employee age. Inside this add employee, I'm going to create the object for prepared statement. Prepared statement stmt. This can be created by using session.prepare method. Inside the prepare method, I need to pass the query. So let me copy paste this query once till here and paste it here. So instead of passing the values like this, let me say question mark, and question mark, and resolve this prepared statement import. Let me import this. It will be the second one, data stack 1. And after this, I'm going to create the object for the bound statement. This bound statement can be used to bound the parameters with the insert statement that we have used earlier. So it will say statement dot bind method. And here we need to pass the 3 parameters. First is the employee ID, then is the employee name, and then is the employee age. So it's EGE and then close. Resolve this. And finally we need to execute session dot execute this bound statement. It will be bound statement. So let me save and run this method again. Sorry, before running we need to call this method. So let me create the object for this class. It's Java connector. Let me say JV, new Java connector, and then call this method jv.addEmployee. Let's say I want to add employee ID as 20 and employee name as say Jack and employee age as 28. So need to use the double quotes here as it is expecting a string. Let me take double quotes. Let me save and now run this. Run as a Java application. So as you can see, now in the result set, you got this as well for the 20, Jack and 28. So that is how we can use the prepared statement instead of passing the value static. In this video, we will see how we can use a query builder. Instead of using this literal statement, we can use a query builder APIs to build the same queries. So let me change the existing code. So I'm going to say statement equal to, going to use query builder dot select. So I'm going to build a query for this one, select star from employee using the query builder API. I'm going to say query builder dot select dot all from, and then the table name from emp. This resolve. And then we will say result. Let me comment this one. This time I'm going to get the result set using the above statement. So I'm saying result set equal to session.execute, execute the above statement, and it should give me the same result. So let me run as a Java application. As you can see, it is giving me the two same rows as expected. So similarly, I'm going to change this method to use the Query Builder API. So I'm going to comment all of that. So here I'm using the statement object and then the Query Builder. So we are going to insert into table name is EMP. So we are going to insert the first value. Sorry, let me delete this. It's not what I wanted. So let me insert the first value. And then we have the column name, that is employee underscore ID, and then the employee ID. Again, the value. This time we want to insert employee underscore name, and the value would be, let me take it to another line, it will be employee name, and then again the value for the age. So it will be employee underscore ID, sorry, age, and it is employee age. So this time I'm going to execute session.execute and then execute this statement. So I'm going to insert one more row here. So let me say add employee. This time I want to add 21. It will be, what name should I use? It will be Jim, and the age would be 20. So let me save and run this as a Java application. This time we need 3 rows. So as you can see, the row for the Jim is also getting displayed. So that is how we can use the Query Builder instead of using these insert statement as it is or the select statement as it is.